but I enjoy it. I feel like I once had a postdoc who, when he left me, gave me a mug that said, "This glass is now half empty," as a sort of statement about my general pessimism. And he told me, I'd never seen somebody get so much positive work done with such a negative attitude about the prospect of things working. So I feel bad about this talk because it's sort of like a negative talk. So the summary of the talk basically is given right here, and I can stop without giving too many details. And the basic gist is that for some of the things that you want to do with Rydberg atoms, the black body decay to, particularly if you're interested in using van der Waals interaction, to other p states, which are ubiquitous, of course, cause problems because this dipole interaction is very strong with these contaminant states. But since I've got a longer talk to give, this is the outline of the talk. I'll give you a motivation for the experiment because we didn't really set out to do dress Rydberg work. And I'll give you a sense of what we were trying to do. And I'll show the evidence for this contaminant state broadening. And then recently we looked some at time dependence to show that the window of time you've got before the contaminant states cause problems is quite small. And then I'll talk a little bit about the theory that Alexei and his student Jeremy have worked on to try to understand it, and then I'll end with some musings. So the motivation was given by the idea of using Rydberg dressing, and we were initially interested in trying to show mechanical effects, and particularly of Rydberg dressing. Basically, the force that you have at this Rydberg blockade distance was something we thought that we could see in our experiment, and mechanical effects due to this stress Rydberg potential hasn't been seen, and we thought it would be kind of interesting to do. And the reason why it should be doable is because if you're off resonance, just like a light shift, the amount of excited state is suppressed, and you get a lower scattering rate than you would get if you were on resonance. And that lower scattering rate gives you a window of time you should be able to do the experiment. And that's what we thought when we were sort of beginning the experiment. Now, we originally did the experiment in the 18S state, which is, I guess, a Rydberg, but like not by today's standards. It's very low end. But we had reasonably good reasons for wanting to do it. One is we were interested in, our real interest before we started thinking about doing dress Rydberg was to look at dissipative dynamics. And if you want to do dissipative things, including Rydbergs, you'd like for the time scale for scattering to be at least on some reasonable experimental time scale. And 18S was a good compromise because it gave a 3.5 microsecond lifetime. We figured we might be able to do some dissipative physics on that time scale. The other issue is that this was on an apparatus that had an optical lattice that was the traditional sort of half micron sized optical lattice. And the physics we were interested in was nearest neighbor type interactions. And if you look at the van der Waals interactions, they're typically, for higher end, way too strong to do anything on a short length scale. And it turns out that the van der Waals blockade radius is about twice the lattice spacing if you're at 18S. And so that was another good reason to pick 18S. And then it also turned out there's a magic wavelength available for the 18S state at around 1064, which is the dipole trap that we have. Okay. So, as I was saying, the goal we have is to look for mechanical effects due to the dress Rydberg potential. And our system is a 3D optical lattice with about a 400 nanometer lattice spacing. And it's a traditional 2-photon excitation pathway off of the D1 line, so the P1 half transition. And this is a system where we can load a mod insulator so we can have 1 atom per site in the system, or 2 or a BEC loaded into the lattice to get a Poissonian distribution. We have some control over the number of atoms per site in this lattice. So one of the things I wanted to point out is that the optical lattice is really important for the experiment. On the one hand, just to suppress the recoil from the absorption due to the Lambdicki effect. But the other important thing that we didn't realize, and some of the proposals to use Rydberg involve the BEC and looking at dipolar, potential dipolar effects due to Rydberg in a BEC. And it took us a little while, shockingly, to discover this as a problem, is that there's a super radiant Rayleigh scattering effect off of just the lower transition. So if you turn off the blue and you just turn on the red, off, even if you're fairly off resonant, there's a gain process that builds in a recoil gradient in the BEC that then runs away, exponentially runs away and scatters the light more and more efficiently. And the reason why we didn't see it to begin with is because our camera direction was almost exactly along the direction of our excitation lasers, and the BEC in the experiment was recoiling away from the camera, and so it got a little what looked heated as it came out of focus. But then when we finally looked at it, and the data was not making any sense, when we finally looked at it from a different direction, we saw that there was this gain process that occurs. And so that competing process, I think, makes it really challenging to do a Rydberg in something that's not trapped in some fairly tight trap. So we control the density of the atoms that are participating in the Rydberg transition by microwave transfer to a non-participating hyperfine state. And then we can control the density from the initial density to 0 just by how many atoms we microwave over. And then our main detection mechanism is we do a Stern-Gerlach imaging of the atoms after the fact and look at how many atoms have been optically pumped into different hyperfine states. And in addition, so that we can have a direct measure of the 18S population, we collect fluorescence from the 5p 3/2 D2 transition to the lower states using a filter to block out all of the excitation light. And so we know that any light that comes from the 5p transition has to have gone through the Rydberg level. So the photons collected are a sort of time-dependent measure of the 18S population. So those are our basic observables: optical pumping to other states and the photons scattered from the 5p state. So the first thing we wanted to do, that you always do in anything in these types of experiments, is spectroscopy. And so we found resonance, because we can find that fairly easily. And if you sit on resonance and you look at the photons collected as a function of time after turning on the light, then which is proportional to the 18S population, you see the population rises pretty quickly. This is for a fairly reasonable 2-photon Rabi frequency or excitation. But if you go off resonance, say something like 45 Linewidths, you see that the excitation is almost comparable within 4 microseconds, which is a very, very short period of time, and we're many Linewidths off resonance. And if you go even sort of 90 Linewidths away, you still get some excitation in a very short period of time. And I should point out that the scattering time just from this simple off-resonant excitation formula is about 11 milliseconds. So, orders of magnitude longer is the expectation for when you would get a majority of the atoms having scattered from the Rydberg state. So we went about doing a systematic study, and we basically just did spectroscopy, and the basic measurements we have are the transition width and the on-resonant excitation rate as a function of the ground state density and the 2-photon Rabi frequency, the excitation Rabi frequency. And the first thing that you notice is that the line width increases as a function of 2-photon Rabi frequency and as a function of density. And this is just a plot of all the data versus the 2-photon Rabi frequency, the measured line width, or versus the density. Another odd thing that we noticed is that the on-resonant rate is linear in omega as opposed to linear in omega squared, the intensity. And the rate is actually slower at the higher density. So it's more strongly saturated at the higher density. Or saturated meaning not the usual saturation in the sense that we don't see any saturation. We didn't at the time have any more Rabi frequency available, laser power available, and so we couldn't go any further. But we didn't see any sign of saturation. And then because this lattice is a double well optical lattice that we have available, we could selectively transfer the atoms into non-participating states on every other site in a checkerboard pattern. And if the physics that we're looking at was dominated by van der Waals interactions, the van der Waals interactions would be decreased substantially because of one over the R6 dependence. And we basically saw no change in any of the physics if you adjust for density. And we also did experiments where we had one per site or increased the density to multiple per site, and there wasn't, as long as you adjusted for density, there was no change in the net results. So if you use the photon collection to give you a measure of the Rydberg density or Rydberg population during the experiment, and you plot the measured width versus the 18S density, you see that all the data collapses onto a roughly single curve. Granted, this is a log scale. And this single curve basically spans, from around 100 kilohertz line width up to sort of 8 megahertz line width, so a very substantial change in the line width. Okay. So the basic observations is that the on-resonant rate scales as the inverse square root of the density, which is different than superatom scaling, which speeds up as a function of density. So this is not some collective effect that we initially thought we would see, because we would have van der Waals blockade within this, very strong van der Waals blockade within this lattice. As I said, the line width is proportional to the Rabi frequency, not the intensity or Rabi frequency squared. And it looks like a strict phasing mechanism, because the on-resonant Rabi rate, as long as you make this Rabi frequency, scattering rate, as long as you make this Rabi frequency depend on the 2-photon Rabi frequency, this scattering rate depend on the 2-photon Rabi frequency, you get the normal Lorentzian on-resonance rate from this expression. And the energy scale is just completely incompatible with van der Waals interactions, which, even at the nearest neighbor spacing should be about 2 megahertz for the 18S state. Now this has prompted interesting conversations about superradiance, and we spent a lot of time at the beginning when we saw this tremendous broadening suspecting that maybe superradiance to other P states was an issue, because if you look at the wavelength of the transition to the nearby P states, it's bigger than the entire BC, or not BC, but atomic cloud. And there was some suspicion that there might be superradiant effects going on. But if you measure the lifetime, you excite them to a low Rydberg density or a high Rydberg density, the lifetime is essentially the same. And we didn't see any effects of superradiance. And so we eventually ruled that out as a possibility. So, as I mentioned, the culprit that we sort of came up with was the spontaneous production of contaminant P states. And I get into a lot of trouble when I say spontaneous and people insist I should say black body, but by spontaneous I mean including black body. Spontaneous means things you don't control. The energy scale is much better. The argument I always made when we were doing the experiment, a lot of the other members of the team, particularly Steve Rolson, was sort of wanted us to prove that this was a problem, and we sort of went about sort of showing it by looking at the scaling and proving it. But the argument I always made is the NPs must be present. If you're in steady state and there's a steady state 18S population, then just due to branching ratios, there's a steady state P population, and so they have to be there. And once they're there, their dipole-dipole interaction is so large, then all hell breaks loose, and you've got a problem for subsequent excitation. Okay. So, and this has been seen and affects other experiments. I give one example here for the from the Munich group, where they see this cascaded sudden death, which is attributed to the same thing, the contaminant P states. So to sort of get a better handle on this, we wanted to plot things as a function of the NP, the density of the P population, which is just proportional to the 18S population in steady state. And we can calculate the 18S population basically from the excitation rate and the measured lifetime of the 18S state. And if you make a very, very, very crude model where you just assume that the line width is proportional to the dipole-dipole interaction, which is essentially proportional to the NP density, and then you take this empirically measured resonant Lorentzian expression here, you can find that the line width should scale linearly with the Rabi frequency and as the square root of the density, and the on-resonant rate scales linearly with the Rabi frequency and inverse square root as we've observed. And if you plot the line width as a function of these two scale parameters, you see reasonably good agreement with just this completely hand-waving crude model, which we take for evidence that these P states are the problem. And just for comparison, if you do the same scaling argument for the van der Waals interaction, both the scaling and the magnitude of the estimate using the crude model basically disagree. So I've had a couple of conversations that have sort of indicated there's some confusion about what the effect is. And I want to point out that this contaminant SP dipole interactions are always resonant anytime a P state is made and you want to excite another S state. And so Thierry was just talking about making it not resonant, but in order to make it not resonant, you have to break the symmetry between the atoms, so you have to address one atom versus the other. If you make a P state, by any means, any other S state that's produced will be dipole-dipole resonant with that P state. And what that means is you can probe the P populations with different S states than were used to make the original blackbody created P states. And so you can look for a cross-broadening effect between different S states. And I want to point out that there are experiments where you intentionally induce a P population and you want to make a spin-half dipole-dipole system like Thierry was talking about. And if you put on a B field to Zeeman shift it, you can isolate that, pair of states. However, this doesn't isolate these blackbody produced states, which are still resonant, so that you don't get rid of this contaminant problem by putting on a B field and making the S to P exchange or P to D exchange process non-resonant for other delta M changing transitions. So in fact, you can do this cross-broadening, and if you, for example, have a pump transition which creates P population through one S state, and then you have a weaker probe transition that you just measure the line width on, you can see that the presence of the probe both decreases the on-resonant rate and broadens the transition. If you look at the on-resonance rate, it's slower when the pump is on. And if you increase the number, the pump excitation or the 18S population, and therefore P, excited P population, you see that the line width increases. And this is showing that this exchange process can occur for a different probe state. We can switch between different probe states and see essentially the same effect with a scaling that looks like the dipole-dipole interaction between the different levels. And that's just showing the different M transitions as probe states for the cross-broadening effect and the cross-saturation effect. And the range over which we could do this measurement is limited by the fact that the pump depletes the ground state population, and you can't pump too hard or you just clean out the entire ground state population. So I started talking about the time window you have available to do the dressed Rydberg experiments. And so we wanted to look at the dynamics, and one of the ideas for getting around this problem was to pulse the dressing on and let the atoms decay out of the P state and then time average over the dressing potential. And so we wanted to look at what happens if you pulse on the excitation light. And for the experiment on a single probe-only transition, this is what we see, is that indeed the line width is narrower for a range of narrow pulses, limited by the Fourier limit, which is shown in red here. Eventually your pulse becomes so narrow that the spectral width is enough to excite the Rydberg atoms, and you have a problem. But the key point is, depending on the number of atoms you have, this time period is extremely short. And the larger the number of atoms is, that time window is much shorter. And it's short for a number of reasons, but one of them is just because you have a large number of atoms and it's a cascade process. As soon as one P state is made, then you get other S states that can be excited with ease. And what I show here in green is just that very, very crude model that said that the line width was proportional to the P population, but made time dependent, so it's a time dependent model. And it's in a way a sort of crude mean field model, and it's much slower, which is sort of the first indication that correlations are really important in this problem. That the subsequent excitations that run away are correlated to be at a particular distance between the atoms. So using the pump probe technique, we can adjust the overlap of the pump and probe excitation pulses and then look at the line width of the resulting transition, and you can see that when the atoms, when the pulses are not overlapped, the line width is narrower, and then when they do overlap, the line width is broader, and there's an asymmetry to the excitation rate, which we attribute to the fast rise of the cascade process, and then there's just the lifetime of the P states, sort of limiting the decay when the overlap is trailing, when the probe is trailing. So we talked to Alexei and company about trying to more accurately model the system, and the first thing that they tried was basically an inhomogeneous mean field kind of model, where you basically take each atom to have its own sort of internal density matrix, and you put in the interactions as these dipole interactions, and then you develop a master equation expression. And it turns out that mean field for the off-resonant dipole-dipole interaction, I think this shows up frequently when you're doing exchange flip-flop interactions. A mean field approach, where you basically replace the spin operator by an average of all the spin operators, doesn't work because it basically always decays to zero. And I think it's because you haven't, the spontaneous emission doesn't break the symmetry to whether you're exchanging with this phase or with a different phase. And I don't know if this is a fundamentally true statement, but it's certainly the case for all of the initial conditions that were tried in the modeling. So you need to put in correlations, and so what they did is develop a cumulant expansion where you basically took into account pairwise correlations by approximating all the three body spin operators by the product of singles and pairs, and then developed the master equation as a function of all these pair correlation functions. And the first thing that I want to point out is that it at least gets an approximate line shape right. One of the things that a mean field model, even if you try to make a diagonal mean field model, it always has very sharp edges on its line shape, because you need to have enough population to broaden the line. But as soon as you don't have enough population to broaden the line, then the transition gets turned off, and so it always turns off very sharply. And once you build the correlations into the system, you can get something that begins to look Lorentzian. So that was a promising success of the model. One of the problems with this model is that even though you build in the two-body correlations, the cumulant expansion approach fails at higher densities that get even remotely near the experimental conditions. And this is an indication of the fact that higher order correlations are important in the system, and you would need to go to a higher order cumulative expansion to sort of properly take into account the correlations in the system. And this is the other issue with the theory is that if you look at the scaling of the excited state population as a function of the Rabi frequency and the density, and you compare it to the experimental equivalent, what was measured was a square root dependence on the density, inverse square root dependence, but the experimental, the theory predicts something closer to a fifth, just kind of empirically, based on the numericals. But I should point out that because of this failure of the second order cumulative expansion, the densities that the theory can go to are only limited to about the equivalent compared to the experimental densities that are available. So now the musings, I'll keep this roughly on track. So very crudely, the take-home message is that instead of this being the scattering rate that you are concerned about in terms of designing your experimental timescale, you have something that's essentially n times faster, because the first p state that's made cascades and creates the opportunity to make more s states. So immediately one tries to think of like, what are the ways around this? And being my glass half empty kind of guy, my thought was like, there's just so many Rydberg states floating around. Bill Phillips always used to say that there are no two-level systems, and rubidium is not one of them. And I think it's when you're dealing with a spontaneous effect, it's really hard to get around. But trying to be more optimistic, there's a lot of options. One of them is to work at lower atom number, because the whole problem scales with atom number. And if you can get to a low enough atom number, then the time window, could be experimentally amenable to doing something interesting. We also thought about quenching the p states to shorter lived states, so basically turning on a laser that coupled the p states to a shorter lived state, and that would sort of limit the problem by broadening the p states, the dipole-dipole resonance between the p and s states. The problem being there is that there's a bunch of p states, and you would have to quench a bunch of things because there are so many p levels that are floating around. One promising approach, particularly in combination with working with the low atom numbers, is to stroboscopically apply the dressing, because you can get a narrowing, and that narrowing is much more effective when you have a small atom number. There has been some discussion of trying to suppress the black body decay by putting it in a cavity. And then the sort of brute force method is just lower the ambient temperature and just try to go to a cold system, which is kind of painful, but would, I think, 100% solve the problem. So the take-home message is that these dress Rydbergs have more time than estimated. It affects, I should point out that it affects both S and P dressing. Like if you do a single photon dressing or a 2-photon dressing, the effect is still there, because there's always black body coupling, strong black body coupling to opposite parity states. You can go to higher n principal quantum number, and that makes all the absolute time scales better. But this sort of scaling with the number of atoms that are participating in your Rydberg cascade process is still there. I think these kinds of correlated errors can affect quantum information applications as well, because if you have some array and you're using for example, van der Waals blockade radius as your controlled interaction to realize the gates, and you have this bad dipole-dipole interaction that's much larger, you can end up messing up like a much larger chunk of your array as you're doing processing. You can always cool. The stroboscopic approaches can help. I think that the correlated dynamics is interesting into itself. It's not a particularly trivial problem, and it's even though it's a dirt effect for everything that we wanted to do in the experiments we were trying to do, it still might be kind of interesting to look at. And another thing is low photon, or low excitation, I should say, low polariton applications are not impacted as much because the atom number is so low. So if you're doing sort of Rydberg polariton at the few excitation level, this effect is there, but is not, extremely detrimental. And I'll end by thanking the people who did the actual work, particularly Elizabeth Goldschmidt and Thomas Bouillet, and Steve Rolson, who's been my Rydberg background. When I don't know anything about Rydberg, I just go to Steve. He explains it to me. Thank you.
Trey, I have a comment on your slide of possible solutions, which is great. I think you're missing one which should be considered, which is if you include this effect you're talking about and do the scaling with principal quantum number, the number of coherent operations you can perform per atom in a time before you get this decay scales as principal quantum number to the 6th power. So you go from 20, you're roughly 20, to 100, 5 to the 6 is a huge number.
Right.
So, I mean, you should still consider that as a solution.
Sure. The reason why I didn't add it into the solution problem, solution list, is because in a way that was already there. You haven't solved the n-atom scaling problem. You've just made all of the prefactors better by scaling principal. Because I feel like the principal quantum number scaling is already part of your toolbox.
It's a big factor.
Yeah, it's a big factor. It's
Sure, but if your goal is to do an interesting many-spin experiment, I'm just saying you can still get there despite the solution without going to a cryostat, perhaps.
Sure. And I think if you look at the numbers, you have to combine it with small atom numbers as well. By small, I mean like 100 or lower, depending on what your experiment is and what time scale you want, and like whether you're talking about large factor suppression below the simple scattering estimate rate. The reason why we didn't say anything more detailed is because anytime we sat down to try to sort of say something, it depended on what experiment you wanted to do, what what regime you were in, what Rabi frequencies you have like capped. It's a many parameter problem. But point taken, going up an n helps.
I'm not sure if the scaling is that big, because if you go higher, especially if you go to tracing, you lose the Rabi frequency a lot. So I think then you need, you have to go close to the resonance again to compensate for that.
Well,
I'm not sure if that's so easy to tracing with
so it simply means you have to just do experiments faster, right? So maybe then tracing becomes not really a viable strategy.
Exactly, that's my point. I think for tracing, I'm not sure if that's if that's so easy to do that.
I think Mark really refers
well,
to
it may or may not be easy, but that's the scaling with principal quantum numbers, n to the 6.
Yeah, but you have to go to closer to resonance and to compensate for reduced Rabi frequency.
That includes the fact that the separation of the levels decreases. That's part of getting back to the 6 scaling. So maybe we can discuss later. I can show you.
I think it kind of depends on your goal. If you really want to somehow make it, if you want to enjoy the time scale with atoms, then of course it becomes, if you want to do this on a long, if you just ask what sort of simulator or quantum computer, I think this is particularly just really fast.
Yeah.
Sorry, but your trace spin interaction also goes down because the Rabi frequency goes down. At a given
It just means that tracing maybe not an optimal strategy.
Exactly. So saying if you really want to scale it correctly, you have to do a bit more calculation than into the 6.
So for this cascade process, comparing dress systems versus resonant excitation, is there something fundamental about kind of weak dressing on the array or on a 2D system that would make this problem worse, or is it just a question of relevant timescales? How quickly the experiment happens?
I'm not sure. Are you asking is 2D different than?
I'm thinking so if you have a 2D array still and you consider a slower experiment where you're doing dressing versus a faster experiment where you're doing resonant excitation, is there something different about this cascade process to the T state?
No, I think the cascade process is there. in all cases. It's just that when you're doing resonant, because the scattering rate is so short, you're naturally normally doing a really fast experiment. And if you're doing a really fast experiment, then you don't see this because you're just doing it faster than the full single atom lifetime, the single atom resonant lifetime. And then if you're doing the dressing, you're trying to do a time scale faster, longer than the resonant lifetime, and this cascade process then has time to kick in.
So the answer is just time scale.
And do you know how many P states are involved in the process? And another thing, did you try like 2D? Or like is the scaling the same in 2D and in 3D? Or could you check that in some?
So the number of atoms that we could see, we can't see the 18S's directly, we can just infer the population by the rate and the lifetime, ranged from fuse to as much as 1,000 in our 40,000 atom cloud. And if you take the branching ratio, which is about a half, then the P state to steady state population should be about half that. The total P state population of all the available Ps. What was the second part of the question?
If you check if the scaling is the same, if you put the 2D.
Right, so the scaling basically goes as the total number of atoms that are excited to the S or to the targeted Rydberg state.
Yeah, if you check if this depends on geometry. Or they recommended.
No, in our system we couldn't do that, but I believe that it would basically just depend on the linear, the number of atoms participating. So in 2D you're better off just because the total number of atoms is less, for a given linear size.
I think actually at some point it would be interesting to sort of do maybe a comparison of dressing versus direct excitation. It depends, I guess, on application that you're
right.
for. It would be very interesting.
My sense.
They're not orthogonal, right? Both of another.
Right. My sense is that if you want to do things that are on motional timescales, you're pretty much hosed, very likely. If you want to do the spin dynamics and you stick to small atom numbers, or if you want to do quantum information applications, particularly if you're using a dipole-dipole interaction for the gate, so that the interaction distance is as long as whatever the contaminant distance is. I think you're going up in N and making sure that the volume of the number of atoms in a given interaction volume are small enough that it should be doable. It depends on everything, the available Rabi frequencies, whatever, but I think for the dressing, you can see from the Munich experiments, they had roughly orders of 100 atoms, and half of the experimental cases on the sort of N decreased time scale ended in a cascade event. So that's sort of like pushing the limits under what their collection of experimental parameters that they're at. But I think you're talking fuse of tens to sort of hundreds, given the typical budget for lasers and.
Okay, any other questions? Any other questions? If not, let's game.